Hi, I'm Shane Brinkman-Davis, and I'm doing this in association with GenUI.co and my own company, ImikImi. And this is a tutorial on how to write a Turing Complete language in 30 minutes. I'm going to be using a set of tools here, so we're going to talk about a few things getting set up, and then I'm going to start the timer. This is an update tutorial to one I did several years ago with a previous open source project of mine written in Ruby. This one today is written in JavaScript. So, we're using this tool called CaffeineEight, which I wrote. There's a little bit of information here for getting installed. You need to have Node.js, and essentially, if you know your way around Node, you just need to install caffeine-8, and then you can use npx and caf to launch Turing, your Turing file, which is what we're going to write in a little bit. This whole file is available in caffeine.8 under tutorials. Tools. CaffeineEight is a parser tool that lets you write parsers, and it's not a parser generator. It allows you to actually just create an object which will do parsing. Nice thing about that is you don't have to create separate files. You can create parsers on the fly. You can modify and update them on the fly, which is super cool. You can have more than one in the same runtime. It's super flexible. It uses a kind of parsing technology called parsing-expression-gramars. You can look that up on Wikipedia. And I'm also not going to use JavaScript. I'm using a programming language I wrote called CaffeineScript. And CaffeineScript lets you write JavaScript with less code than any other language. Right now, it takes less than 3x the same amount of code in CaffeineScript to write the same code that you would write in JavaScript. But sometimes it's as high as 5x. It's pretty dramatic. And you can read more about that at caffeinescript.com. But now we're going to dive right in. I do want to emphasize that this really is just all JavaScript. I'm writing it in CaffeineScript because it takes up less screen space, which is great for tutorials. I love CaffeineScript because I can write JavaScript much quicker than JavaScript, pure JavaScript. It's also less dangerous than writing code in JavaScript. You need less linters and other tools to make sure your code is safe. But really, it's just JavaScript. And in fact, you can use CaffeineEight in JavaScript. It'll actually look great. It'll run well. But I'm not going to go into that in this tutorial. So, next, background. So this is what we're doing today. We're going to build a Turing Complete language. Why do we care? Turing Complete languages are computationally universal. And in fact, it's probably the most important concept of all of computation. A Turing Complete language can do anything any other Turing Complete language can do, which includes all programming languages you've ever known. It includes all computers you've ever known, with the special exception of things like quantum computers, which we'll set aside. But if your language is Turing Complete, it can do anything Java can, JavaScript, Ruby, Scheme, Clojure, whatever. Turing Complete language can do anything any other programming language can do. And we're going to write an entire Turing Complete language today in 30 minutes. In order to prove that your language is Turing Complete, it needs to be able to emulate a Turing machine. This all extends from Alan Turing's work almost a century ago, and it's great stuff, but I'm not going to get into it too much, but we're going to talk a little bit about what a Turing machine is. We are not going to actually strictly emulate a Turing machine today because we don't really need to. We can do one step slightly more removed. But this is a nice little visual of what a Turing machine looks like. That roll of tape is to emulate memory, and in fact, a real Turing machine has an infinite memory. And it moves along the tape, and it reads and writes symbols on the tape. The tape allows you to read and write, and the symbols, we're just going to call them integers in our program. This is a little bit of detail here about the Turing machine, and this kind of sums up like the entire Turing machine. But I'm not going to go into that today because that's not super critical. It is in this README file, which is in the Turing tutorials in CaffeineEight, in the CaffeineEight repository, which is linked to above. It's on GitHub if you want to do it. GitHub/caffeine-suite. And from there, you can find caffeine-8. So as I mentioned before, Turing Complete languages, pretty much all programming languages you've heard about are Turing Complete. But JavaScript, Java, Ruby, C, C++, Lisp, Scheme, Go, Erlang, Elixir, those are all Turing Complete. But there are other languages we use that are fairly expressive, but they are not Turing Complete. And that is CSS, HTML, XML, JSON. None of those are Turing complete. And I think that's very significant. I think those are problematic constructs because they're not Turing complete, because you can't do things in them. So we're going to write something that's way more powerful than any of those. So the bottom line, and this is the end of the file, in order to write a language that can emulate a Turing machine, you really only need three things. You need an effectively unbounded memory. There is no actual infinite memory in the real world, but a memory which in principle could be unlimited if your machine was bigger and bigger. You need to have the ability to have conditional executions, so you can test a value and you can do one thing or another, and the ability to have unbounded iteration. Your machine needs to be able to run for as long as it needs to run. So we're going to write a language that lets us do this. In fact, we're going to do something a little bit nicer than that really, really strict minimum. We're going to write a language that you could actually use. So now we're going to dive in. That's not where I'm going. I'm going over, you notice this is VS Code, but I'm just learning VS Code, and so I'm still a Sublime Text fan. My instructions suggest creating this little file, which then we can test running, npx caff turing.caff, and we'll see hello spit out. Caff is the caffeine script runner. It'll run a caff file directly without having to convert it to JavaScript first. It'll take care of converting it to JavaScript and then run it through Node. But for our purposes these days, you just run caff, and npx helps us figure out what the caff file is, so you don't have to worry about paths and things. So we are going to start by parsing the language. And then we're going to make the language actually work. And so now we're going to start the timer on my watch here, bring up a stopwatch and press the start button, and we are on the clock. Make sure that I really have this right. I need a better timer than this, but there we go. That looks good. All right, here we go. So first of all, import art standard. This is just my standard lib. If you already have CaffeineEight installed, you'll have this available to you. It just has some handy things like loggers, which we're going to use. We're creating a class. So this is how you create a parser. CaffeineEight parser. So that's all you need. Oh, sorry, we want to keep that and get rid of that. These ampersands are requires. If you know Node or JavaScript, this is how you import a file with Caffeine script. It's a little smarter than require because it has a little bit of a search functionality to it. But these are actually just going to pull in some npms, they're actually called all lowercase with dashes. So art-standard-lib or caffeine-8. But ampersand is a little bit smarter. It knows how to search and allows you to be a little more consistent about your capitalization of things. So we're going to do, just to get things started, we're going to do just the bare minimum here to make it parse something. I'm just going to parse anything that is word letters. So that right there is a parser. When you write a parser, most parsing tools, you set up rules for parsing. And a rule is basically a named pattern. This CaffeineEight looks for you to name a pattern called root, which is where you start. It's the root of all your parsing. And then you can establish everything in terms of that. CaffeineEight allows rules to just be a regular expression. So that's what I've done. I just put in this regular expression, which finds one or more word characters. This little .repl at the bottom is going to take this whole class after it's defined, and it's going to invoke the repl function on it, which comes down from CaffeineEight parser. REPL, if you don't know already, is at least used in the Node world, as a command line interactive shell. So this will fire up a nice little command line interactive shell that lets us test out our parser. So now we run it again, and instead of saying hello, it now has this little prompt. It's Turing. So if I type in hi, it says, great, I matched it. I matched it at offset 0. It's found the string hi. But if I type in something that's not a word string, like that, oh my gosh, I'm going to pause the whole tutorial right here because I have this patch already done. It just isn't quite deployed yet. That gives us good errors, not that ugly error. Be back in just a moment. Do, dee, do, 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 dee, do, do, do. All right, and we're back. And I've resumed recording. We were 3 minutes in. Now we're going to run this again. And again, we say a word combination. It says great, matches that. And now if I put in something that doesn't match, oh, much nicer. Parse error at row 1, column 1, right there. It was expecting a word to continue, but it did not find it. Great. Let's continue. So now we're going to start cramming through stuff. So we need to be able to match, we're going to match statements. It's going to look a little bit like a mishmash of languages, but kind of Ruby and C and C++, those kind of category JavaScript. It's going to be a little bit like those things, but a little bit different because I'm going to make it concise. So statements are going to be, do I want to show you all that right away? Probably. So the first thing about parsing expression grammars is that you have to match even your white space. You have to say exactly how you're matching everything. So we're going to go a little simpler. We're just going to go straight to an expression. We're just going to match one expression, and I'll come back in and we're going to add statements here. Let's do an expression is a value. And a value is, I am copying over code, I must admit. So, again, these are rules. So we got several rules here. Wait a second, these are all rules. Thank you. So a root is an expression is a value, and a value is, and I'm providing a regex. This might look a little bit weird to you. It's got 3 slashes. 3 slashes means we're starting a regex block. And a regex block in CaffeineScript, which is similar to CoffeeScript, allows you to have multi-line regex, allows you to put comments in your regex, which is super nice, and it ignores spaces. So if you want to match a space, you have to escape it. But right now, it's just going to say, optionally match a dash, and then match 1 or more 0 to 9 digits. Because we're all going to be dealing with integers here. So let's see what our REPL thinks about this now. We restart it, and we say, hi, that's no longer legal, but we can do a number. Great. And in fact, that is our values. That's super. So next we're going to get right in there and do operators. Because that's really where we want to be able to do interesting math. An operator expression is also pretty simple. It's going to be an operator that's going to be an expression. And we're going to do it this way to start with, but we're going to fix this a little bit later. So what's underscore? Underscore is actually just another name. And underscore is going to be it's going to be this pattern. It's going to be spaces or new line or a dollar sign. So it's going to be something that separates things apart. And then it's going to be followed by any more new lines or spaces that we find. It's going to suck those all up. So it basically is white space. It requires some amount of white space. But sometimes we might be at the very end of the file, and that's okay. So that's why I put the dollar sign in as well. So now we can, in fact, I'm going to put these a little bit nicer so they can just be lined up nicely. Now we can match operator, space, expression, space, expression. We're going to do prefix just because it's a little easier to deal with. We can certainly do infix or postfix. If you don't know those terms, it means do you write your math as 1 plus 2 or plus 1, 2 or 1, 2 plus. This is infix. The operator is inside the 2. Prefix, the operator is before. Postfix, the operator is after. But we're going to do prefix for a couple of reasons. It's a little easier to do quickly. Now we need to do our operator, which is also going to be a regex. Our operators we're going to match are less than or equal to, greater than or equal to, equals, or a mishmash of plus, divide, I'm doing this in totally random order here, all the basic operators. So this is just a regex that matches one of those operators. So now we should be able to match operator expression. So there's something else interesting that happened here, right? An expression can be an operator expression or a value expression. There's a little bit of CaffeineScript magic going on here. What this actually is an array. If there's one value, it'll become a single value, just like you'd expect in JavaScript. But if you list 2 values, where one was expected, it'll become a list, or an array in this case. So it just implicitly becomes an array here. It's an array of 2 strings. Oh yeah, these colons, these are strings. They're the same as this in JavaScript. But they allow you to do word strings, which is great. It lets you have less syntax. This also is a string block, which means that the string can take up multiple lines. It is the same as this. So let's test it. So we can still batch numbers, and we can do +1, 2, great. But we can't do 1 + 2, that's not allowed. Can't do 1, 2 plus, that's not allowed. But we can do +1, 2, and we can also do, the super cool thing is, look, an operator expression is an operator followed by an expression followed by an expression. So look at this, +1, 2, 3. Starts a little magic there, but basically what that ends up being is that'll get evaluated first and become 3, and then it'll become +3, 3 once we have actual computation going on. So continuing on, that is operators. In fact, that is all of our operators right there. We are fully functional for operators except for actually making the code do something. We'll get back to that. Now, we need to be able to have a memory. We need to be able to store and retrieve values. So let's go ahead and do that. Store get and store set. So let's just go down here. Store set is something, store get is something. We're going to fill both these in. Store set is going to look a little bit like this. So it's going to be, we kind of have, initially, if we're just doing it purely like, we can make this nice and simple like this. It always needs to be equal to a space and then an expression. So if we want to just do something that is purely like Turing, which is to say it's just a tape that's infinitely long and you access it by your position, we can just do it like this. We need to be matching the set before get. We can just have, all of our expressions are going to return numbers. In fact, we're not going to return anything but numbers in this hypothetical language, just integers, positive, negative, or 0. And so this is just going to be a memory where we say at some position, our expression computes in a position, we will either assign a value or we will read out a value. That's perfectly good. That would fully qualify us for Turing completeness. But in order to make programs that are actually readable, it's nice not to hard code memory locations. And so we're also going to offer an alternative, which is we're going to do this. We're going to say a variable equals an expression, or just a variable itself. And a variable looks like this. A variable is something that starts with, we're going to ignore cases on variables also. It starts with, yes, underscore A to Z, and then it's followed by, optionally, more word characters. In a moment, we're going to have to alter that definition, but that is sufficient for right now. So we have a variable. We can read and write variables. I am going to do a couple things here, though. I'm going to put in optional spacing here. So you can have space or not around the equals, and similarly here, and here, and here. We're going to streamline this a little bit later. But so underscore is the name of the pattern, and then question mark says optionally match that. It looks a little bit like regex. Load it back up, and now we're going to say foo equals 1, 2, 3. That parses. We're going to say position 1 equals 1, 2, 3. It doesn't parse, so let's go figure out why. All right, so we have an expression. Let's just store set. And, oh, I know why. Haha. So check this out. Parses, I did not allow us to have a space in between right there. So I think I'm going to do it like I did in my little mock-up before I wrote this, like that. So now it really can be new lines. It can be anything between the open bracket and the equals. Now we should be able to do this. 0 space equals space 1, 2, 3. That looks great. And in fact, we should be able to do like a percent reading a variable, foo, all super groovy. All right, so now we have a data store. at least the way to parse it. Now, moving right up the list, we really have only a couple more things to do. We need to have unbounded looping, and we need to have conditional execution. Let's jump in with conditional execution. How about an if expression? An if expression looks a little bit like this. If expression, then expression, and we're going to use a keyword, and we're going to do sort of that kind of style of programming language. Now, as what I want to actually do a little bit of something, I'm going to make a new thing called an underscore expression, which is only slightly different from an expression in that it has an optional white space in front of it. That's going to start to streamline our definitions here. So I'm going to actually use underscore expressions here, which means that we don't need to have these underscore question marks in front of them, because we're using that pattern over and over again. That just is going to start simplifying all of our stuff. So now that's an if expression, then expression end. And that's pretty cool. Strictly that's all we need because we could express it twice, but we're going to make it a little bit nicer. Let's go ahead and put an else in there too. So now remember, this is alternate. We can match either of these. So first it's going to try to match the whole thing with else. If expression, then expression, else expression, end. But if that fails, then it'll try to match it without the else, which is great. That works well for us. We can go there. That little tool I was just using to resize my window is called Divvy, D-I-V-V-Y. It's awesome. Check it out. All right, if expression. And that actually is all we need to parse if expressions. Let's try it out. If foo, then bar, end. I lied. There's one little thing we need to fix. We are now using keywords, but we also have variables which could match keywords. We need to make sure our variables don't match keywords. So, not matching, if, or, then, or, else, and that's all we have for keywords so far, I believe. If, then, else, and end. We need to make sure we don't match any of those, and specifically, we're not going to match any of those with a word end. Try it again. If foo, then bar, end. I think we might have a space matching problem too. Let's say foo equals 1 to 3. That likes it. All right, so yes, we do have a space matching problem here. So I'm just going to put these back in right now. We're going to further improve this, but I was doing expression which did not match a space after it, so it expected the then to be immediately after, which we know is not going to work. So I'm putting conditional spaces at the end of those expressions. I'm not going to do an underscore expression underscore rule because you'll see in a moment I'm going to do something a little more general purpose than that. If foo, then bar, end. Now it expects to be able to read foo and bar out of our memory, but it parses. That's great. So now we have if expressions fully implemented. Last one, while expression. We need to have loops. Let's do it. I'm just going to do a little copy paste because if you've ever looked at a while expression, it looks like this. I'm going to do just to be consistent with the way I expect things. It's a while expression, do, somebody, end. So now that's super groovy. Let's test it. While foo, do, bar, end. It parses. There's one less thing we kind of want. We'd like to be able to do more than one step. Right now, we don't really have a way of doing a sequence of actions. We can technically chain two things together with a variable expression, and if we just ignore the result, that would chain two actions together, but that's going to get kind of convoluted. So if I say editor here, this is built into the Node.js REPL framework, and we're just leveraging that, so that gives me a really simple little editor. But if I did 2 lines, like 1, 2, 3, 1, 2, 3, it's going to say does not parse, because we're not expecting more than one expression, which is where now we're going to change this last little bit. Instead of saying expressions, we're going to say statements. Statements in our language are actually really trivial. The little background noises, my boy is in the background doing Minecraft. All right, we're going to take expressions. This little plus is like a regex plus. It says match the rule expression one or more times, followed by a conditional space rule, a white space rule. Again, this underscore is not a special name. It's just my pattern for dealing with white space. When I'm making a parser, I'm going to make an underscore rule for the white space I want to ignore. A typical thing I'll do if I'm writing a full language is I'll actually put in the comment parsing as part of underscore. So wherever the underscore shows up in my source, which you can see it's all highlighted here, it could in theory also match comments. We're not going to add comments to this language, but you could add that as one of the alternate rules for what underscore matches, and then you would match comments, and it would work great. This is all we're doing for statements. So the root is a bunch of statements, and a statement is one or more expressions followed by some extra space. We're just going to gobble up all that extra space. And given that, first of all, let's make sure we didn't break anything, which I don't think we did. 1, 2, 3. And now we should be able to do what we just talked about, which is 2 lines worth of expressions. 1, 2, 3, 1, 2, 3. Great. Now we can use this statements, and we're going to just go ahead and replace these. Anywhere I'm doing that combination, we're going to have to replace it with statements. It's a little weird to see statements inside expressions, but really our statements in this language really is an expression. And as you'll see when we implement it, a statement is what I'm going to call a sequence expression. Since we have side effects in this language, it just is execute several expressions in order and return the result of the last one. So it's still an expression in the sense that it returns the last result. It just ignores the results of the previous ones in a list. Now we have while loops and if statements that work much like other languages. Now we can do something like this. I'll restart. And we could say while I is less than 10, foo equals I equals I plus I1, because we have prefix, end. Don't you hate it when it doesn't work? Oh, I know why it doesn't work though. Can you see the bug? It'd be nice if it had slightly better errors there, but I think I sort of see what it's doing. It's expecting, see here, down here, while is matching multiple statements. So these are all becoming part of the expression for the test. But it gets down here and it does not expect to find an end. It either expects more expressions of all these different types, or it says, where's my do keyword? That's what's missing. Let's try it again. Editor. The annoying thing about this editor is like there's like no editability. It's like one line at a time. Do, forgot our do. And now we can do these next 2 lines and then it still doesn't work. Let's do a shorter thing. While I do bar end. Yes, it indeed does not like what we're doing here. Let me double check on why on my notes. So while statements, and the statements is going to look for one or more expressions possibly followed by, and we had basically, right, we had this before and this was what was working. While foo do bar end, and that is happy. But when we convert it to statements, it doesn't like it because foo do bar end, if foo then bar end, it likes that one. So why does it like if statements then, oh, gosh darn it. Guess what? We have a new keyword, a couple new keywords, while and do. It was thinking it was matching variables. So while foo do bar end. Great. Just for verification, while foo do foo equals 10, 23. How about foo equals foo minus foo 1? And we wanted to test multiple statements here, so we'll just say bar equals foo plus foo bar. And yay, it all parses, it's all happy. So now we have our Turing Complete Language. I think we got everything. All right, But now, we are now parsing a Turing Complete language. That is super cool. Let's make it do something. That's where it gets super fun. All right, flipping over my notes. It's not going to be that much more complicated, as you'll see. So, what you can do with Turing, with CaffeineEight parsers, is you can, each one of these rules will construct, when it parses, a tree of objects that match these various structures. You can attach, each one of these has its own class, basically. There's root has a class, statements has a class, expression has a class. And in fact, each variant has a class, but we're not going to get into that right now. So actually, each one of these variants, these are the expression as an if expression, expression as a while expression, those are each variants. Each one of those has its own class as well. You can attach custom methods to these classes. We're going to say evaluate. And right now I'm just going to return 1, 2, 3. It could be anything, but REPL looks for an evaluate method and invokes it if it's present. Right now it's just returning the parse tree, which is fine. But really we want to do something, right? So if I say it outputs 1, 2, 3. If I still do something illegal, it'll give us the error stuff. But notice it's always going to output 1, 2, 3 right now. Not very interesting because I hard coded it. All right, let's go on down. So what we're going to do is we are going to go here. Here we're going to do something a little bit special. At is the same as this in JavaScript. In fact, I could write this dot. That's legal. But this is just cleaner. Comes from CoffeeScript. We're going to make our storage, which is going to be an object. That's just like JavaScript. This question mark equals is kind of, it means set this value if it doesn't exist. And existing means it's not undefined or null. So if Turing store is null or undefined, it's going to get set to that. Otherwise, it's going to be left alone. For some, depending on our uses, we could consider just assigning it that right now. But we want to actually have an ongoing persistent memory store in our REPL. And our REPL creates one instance of the parser and then uses it over time. And so we do this, we can read and value values over time in our interactive shell. So we're going to do this. Statements dot evaluate. So we're grabbing the output here, but that's only because I want to just log store. I want to see what the store is after each time we run something. Otherwise, we really could just say, we don't have to capture this at all. We can just do that. Because one of the things about functions in CaffeineScript is much like the language we're writing ourselves right now, a sequence of statements is always an expression, and it always returns the last value. And so a function is a sequence of statements, and it does each of these statements, and then it returns the value of the last statement, which is what we have right here. So statements needs to be able to do evaluate. Now that we're calling evaluate, we have to make sure all the sub things know how to do evaluate. Evaluate on the statements looks like this. We're going to go for each expression in our expressions. Tell you what that means in a minute. Last equals expression.evaluate. So each is a comprehension in that it takes in a value, which is either can be a plain object or a plain array, or null or undefined. And if it's an array, it'll iterate through the array. If it's an object, it'll iterate through the object's properties. In both cases, it returns the value as the first parameter. We could also do this, which will grab us the key of each iteration. On an array, it's going to be 0, 1, 2, 3, 4, and an object, it's going to be the property keys. But right now, we don't really care about those. We're just going to grab the expression. Notice this is plural. So whenever you're matching one or more of something, CaffeineEight is going to create an accessor for us, a getter. And this getter is the plural version. So it's expressions, plural. And so it does that. And it will fetch all of the nodes in our parse tree which matched. So if it matched several, it'll be an array. It's an array of several results. But it could just be one. So we're going to go through each of those expressions, evaluate each of them. We're going to capture the value of each in this last variable. In CaffeineScript, variables are declared, or defined, like you would in JavaScript with a let. the first place you assign them. So that's declared within this scope because I assigned it right here. Starts out as just a non-initialized value, and then we're going to return it at the end here because we want to return the last one. Great, that's statements. That is all of statements. We could do, I'm going to put this here. I don't think I need that guard because we're going to have that guard elsewhere, but we want to always have an integer. And so if we ever return null, if this ever returns null or undefined, this question mark says, return this value unless it's null or undefined, and then return that value. So we're going to always return a 0 from our list of statements. It's just a guard. I think if all of our other expressions return 0, it'll be fine. Return integers. I'm going to come right down to value here. So value is the one thing of these guys, which actually is going to get a little bit more code. Evaluate. And this one's going to be kind of interesting. We're going to do this. Let me double check I got it here. With a little bit of trickery, we're going to use JavaScript's eval function, and we're going to say eval toString. So a node in the parse tree can be converted to a string, which is the exact sequence of characters it matched in the source text. In this case, it'll always be a negative sign, an optional negative sign followed by digits. So if we evaluate that, it's completely safe. It's always just going to be an integer. It'll evaluate it and return an integer. So I think now we can actually test this. There's a minimum we can do to test this. Nothing else is going to work except for a single value or a list of values, but that should work. So now instead of always returning 1, 2, 3, expression value isn't a function. I think that is right because expression doesn't know how to do evaluate. We have to make sure all the way chain down. Evaluate. And the evaluate for an expression is actually really simple. It's matches sub0 dot evaluate. Like I said, whatever you have a rule, it's going to create an accessor for that rule. So statements here is just a single thing. So the plural is actually kind of relevant. The fact that it's statements means I can access the statements. I'm at 30 minutes, guys. I'm going to go over, but we are so close. Expression. In this case, matches returns all of the matched nodes, whatever their names are. And so we're just grabbing the first one, and we're going to evaluate it. Now it should work. 1, 2, 3. Expression and evaluate is not a function. Evaluate, evaluate, evaluate. Not calf. So it says that. So we got to roll things back up. Why is expression not doing? Yeah, so that's not going to tell us very precisely where we are here. This is a place to inject. If anyone knows about source maps, I am generating source maps correctly, exactly correctly. I've validated them left, right, and center. I don't know why Node won't use them. I'm generating them exactly correctly. I used all of CoffeeScript, which is which does this, and it does work for CoffeeScript. And I still don't know what I'm missing. I don't know why it's not using my source map here. It should be a source map. It has the line numbers wrong. If I open this file, it's going to put us here, which is not the right spot. Evaluate, evaluate, evaluate. So I'm going to do the age-old thing, which is we're going to say, we're going to put in a couple of functions here. We're going to put a couple of log statements here to sort of see what's going on, right? Right. Okay, we get to statements 1, but we do not get down here. And I know why. So it's saying that that is not a function, which they're correct. And now we know why. Because you notice that what I noticed was this never got called. That's because it's down here. In my old... So CaffeineEight is a re-implementation of Babel Bridge. Babel Bridge was written in Ruby. Ruby is a little nicer than JavaScript for OO. It just is. And one of the things with Ruby is I can do if you invoke a method that doesn't exist, I can automatically generate that method for you, which allowed me to do cool things like I could automatically generate evaluate for each of these nodes to return the first rule matched or something like that. And we can kind of do that in JavaScript. I mean, we can't automatically generate that, but we could have made a base class and we can inherit it. I wanted to keep this simple. But in my previous example, it actually was simpler. It did actually automatically evaluate the right thing here. Anyways, this is still pretty simple. Expression.evaluate. Now it should work. 1, 2, 3, yes, but also 7, 6, 8. Groovy. Now let's cruise right down. We just got to put the evaluate on each of these different nodes, and then we will be great. Those ones are already done. I'm going to come back to those. I want to do the stores. I want to do the operators. Evaluate. So now we're getting into the weeds a little bit. So I'm going to do this little trick here, left and right. You notice we got two things. We've got expression and expression with the same name. You can give them labels, left colon and right colon, and then we can access them as at left and at right. Remember, that's the same as this dot left. And here we go. We're going to take our right. This is what we're looking at. So we're still going to use the eval trick, and we're going to say we're going to evaluate left.evaluate operator So what that looks like, that needs to be, we're generating JavaScript because we're plugging it into the eval function. We could have done like a switch statement and switched on the operator to all the different operators and do the right thing, but this works out the same. And for our example, it's super easy. At left and at right is accessing our left expression and our right expression. We're putting the operator in the middle because it's infix rather than prefix or postfix. And then we're telling JavaScript to evaluate it. The other little magic here, these are interpolation, I believe is what they call it. In JavaScript, you need to use this, you need to use these ticks, and you use $signs with the new JavaScript that supports that, but it's the same thing. And at operator here is getting the parse tree node of the operator matched. But remember, each node implements toString, and so this is just a JavaScript concatenation. Strictly speaking, this actually looks like left.evaluate that space plus that plus space plus that operator plus quote quote plus right.evaluate. So that's just a normal JavaScript string concatenation, and JavaScript will automatically invoke toString on your object. Great, we have our value. The thing is that some of these compare comparators, and they're going to return a true or a false value, and we want to only ever return integers because we want to keep our system our whole thing really simple. So what we're going to do is we're going to do this. Switch when v is a number, then just return v. When v is true, then 1, else 0. So here we go. If v is true value, we're going to say 1 is true and 0 is false for our sense of logic. I just realized we didn't do ampersands, we didn't do ands and ors in our operators. I think we can just add them, just drop them right in, but since I didn't pre-test it, I'm not going to show it to you right now. Java does actually also think that 0 is false, which I think is a bad concept. Ruby does not. But we can leverage it here because we're in Java land. So, JavaScript land. So, 0 is false in JavaScript, and anything not 0 integer is true. And so, if we just drop in ampersand, ampersand, and pipe for and or, I think it would just work. So now this is going to return 1 for true, 0 for anything that's not true or a number, and number is v. This is operator is unique to Caffeine script. Is means either directly equal or instance, or not instance of, direct prototype of. So it's not anywhere up the instance tree. It's this is an direct instance of number. So either v is an instance of a number, or it exactly equals true, and that's the result. In this switch, you can say switch v and then go to and match v against multiple things, but in this case, we want to match it. This is the way it needs to work right now. So that should work for operators. Let's try it. Plus 1, 2. That is super exciting, right? Plus 1, 2. Plus 3, 4. Plus times 2, 6, 9. So that's going to be 6 times 2, which is 12, plus 9, which is going to be 21. Love it. All right, that is super, super sexy. All right, we are almost there. Now we're going to go up. Store, get, and set. That is the next most exciting thing. Evaluate. So we're going to be accessing the part of the Turing store that we put in on our parser. The reason why we put it on at parser is because any of the nodes in this result set can access the root parser. And for parsing purposes, you can actually instantiate multiple different parsers, Turing parsers in the same code. So you can even, if you want to have more than one Turing machine running in our code, we could just instantiate multiple parsers and each one would have its own Turing store. So we are getting, so we're going to read it out of our Turing store. Remember, our Turing store is an object, so we just need to provide it a string or string equivalent. Here's how we're going to do it. At variable, which if we matched a variable, it would get stored in the variable accessor. Otherwise, it's going to be null. Or actually, it's going to be undefined. So variable, but if it's undefined, then we're going to go and access statements. And so for consistency, in fact, actually, we didn't ever change this. We want this to be statements too. I believe is what we're going to do for store get and store set. I guess I did have an expression in those. That's fine. We'll do statements here. Those could be. That's right. Always, my statements are always bracketed. You notice the statements always has a specific end thing that happens after a statements list, and that's how we can get away with them being as many as we want. If we put it where we're not bracketing, where we don't have a terminator, then we run into the parsing issues with the fact that operator can match 2 expressions in sequence. So that's how we're keeping it simple. Anyway, we'll just go and access it as statements. We'll do what I did my test run up. I labeled it index, so we can, which is more accurate for what it is. We evaluate it. Again, I'm not sure the R0 is strictly necessary, although it could be. Right now, no, actually, we have non-integer stuff because we can do this. Dev 5.2, right? Sorry. Dev 5.2. It's 2.5. So indexes should be whole integer units. So we're ensuring it's a whole integer unit there by doing pipe 0. You can do that same thing in JavaScript. It's a little JavaScript trick. And we're always going to, since we have an unbounded memory, we might be reading out something that was never written, and we're only allowing integers. So this always just guarantees that our result is, we're reading out a legitimate value that was written or 0. Great. So that is evaluate for store get. Store set is going to be pretty similar. And this is how we're also going to do index here. And then this becomes the same thing, right? It's variable or index at evaluate. And that was exactly the same. The only thing we're going to do here is I'm going to call this, I'm going to also put labels here. I wouldn't have to because it's the same in each pattern. But when I have multiple patterns, I really like to label them so I can change the pattern up but still access the same thing. So here, though, we're going to do this. We're assigning expression.evaluate. So it's pretty simple. I mean, look at this. It's just accessing the store either with a variable name or with an evaluated number truncated to an integer. And then we're either reading it out or writing it in. Let's see if store get and store set work. This is when it starts to really get exciting. Foo equals 1, 2, 3. Can I read property evaluate of undefined? Fair enough. That's because it's not expression, is it, folks? I labeled it. If you label it, then it means it will not go into its rule name. Foo equals 1, 2, 3. Notice that assignment also returns the value assigned, which is actually just like JavaScript. But now if I read foo, we can read it right back out. Foo equals plus foo1. Look at that, folks. That's exciting. Let's just check the other things. So if I put it at an index, then our store now has at index 1, it has 1, 2, 3, and at name 1 equals foo. We get away with that because JavaScript allows us to shove numbers in and out as properties, and they just get converted to and from strings. Since we're dealing with whole integers only, it's always unambiguous. It's just going to work. And we don't allow our variable names to be numbers. So it all works out pretty nicely here. That is store get, store set. Now all we need is if and while. Let's do it. If, at statements dot evaluate. And I'm going to actually call these, I'm going to do some labeling here too. Test, body, else. And so we're going to actually say if test.evaluate, remember JavaScript already accepts 0 as false, otherwise everything else is true. Then body. Another thing I wish I had Ruby for is Ruby lets you define a function invocation operator on an object. And so I could actually just say invoking one of these objects triggers evaluate, and then I could just stop having redundant evaluates everywhere. Can't do that in JavaScript. Or else.evaluate. I am going to put an or zero, question mark 0 at the end because of this. And actually, I think I can just do it like that. So body should always return a legitimate result because it's just statements, and statements should always return a legitimate result. But this says, if else exists, then invoke this method on it. Otherwise, return undefined. So if else does not exist, in which case there's no else statement, we will return 0. Let's try it. We're almost there, folks. So if we're going to say foo equals true. I'm going to say if foo, there's no such thing as true. True is a value that we read out of the store because it thinks it's a variable name. And since it was never assigned, it is 0. We can make true if false in this language. Foo equals 1 to 3. Great. If foo, then 111 else 222. We're going to do, we'll do else for now. End. So look, it is that. But now if we say foo equals 0, and then we run it again, it's going to return 222. Now let's do one last thing. We're going to take off the else statement, in which case it should return 0. Groovy pants. Last but not least, and remember, while loops were already super simple. We want to put our labels in. I like keeping things super consistent across everything if possible. Consistency, someone once said consistency is the mark of a small mind. That's total BS if you're a programmer. Consistency is the bread and butter of the master programmer. So we're always going to have tests. We're going to have a body. We're doing while. While this is true, loop through the body. Our while statements already return the last return value. That's how while statements work in CaffeineScript. However, it's possible that we'll not iterate ever, in which case it will return undefined. So we're going to put a question mark 0 there just in case we iterate never. So now I can say while 0, and we do have do 1 to 3 end. And that should just immediately return 0. Now let's do something interesting. Stop equals 10, I equals 0, while I is less than stop, but it's less than I stop because we're prefix. Do sub I equals I, and then we're going to say I we need to make sure I equals I plus I1. Now that looks a little funny because how are these statements being parsed out, but I think it'll work. Presto, it did work. Our rules are such that is actually unambiguous because you can't have two, because our assignment only expects an expression, it does not expect statements. Notice I was mentioning that earlier, that we're only going to match statements when there's a end bracket to tell us when the statements should be ending. So there we go. We assigned 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Super groovy pants. Now we're actually done. That is actually a Turing Complete Language. So I'll check the time on that in a minute, how much time that was, probably closer to 40 minutes. But while we're here, I do want to show you something cool. And I'm going to do it this way. We can do it with an interactive shell. I guess it doesn't really matter too much. So So I'm in the editor, and I just pasted in this code. This code will run in our language. And what this code does is it finds prime numbers for us. In our language, we got a real program doing real stuff. We set a cap at the maximum prime we want to find. And then it goes through, and first it initializes our array of primes to all true values, which is just the value 1. Value true, which is, it could just be all the value 1s, but just to make the output nicer, I made it just the value that we're at. So it just goes 1, 2, 3, 4, 5, 6, 7, 8, 10, just like we just did with our previous example. And then this is the prime sieve algorithm. So then it walks through the primes that we have marked off, a potential prime. So right now we marked off everything from 1 to 30. But now it's going to start at 2, and it's going to mark off everything that's a multiple of that number. And then it will advance to the next non-marked off number. We're marking them off by setting them to 0. So now we run this, and there's our results. 0 means it's not prime. Otherwise, 0, 1, 2, 3, 0, 5, 0, 7, 0, 0, 0, 11, 0, 13, 0, 0, 0, 17, 0, 19, 0, 0, 0, 23, 0, 0, 0, 29. And then we have our values max, prime, I, and j, which was the locals we were using to do all of our work. Notice that j ended up on 58, which happens to be the next multiple of 29. So it's super cool. Prime sieves are super fast too. So even though this is a very interpreted language, we could probably set it to 10,000 and it would probably still be like quite fast. There we go. That is the whole example. Sorry, it took a little more than 30 minutes, but it's still pretty darn fast. You can write a Turing Complete Language, particularly using something like CaffeineEight that lets you write a parser really easily. But you could even do this with other parsing generator tools. It's going to be probably 3 times as much code, probably even more than 3 times as much code, because CaffeineEight is also very streamlined for syntax. So it's probably going to be closer to the 5x. It's going to be about 5 times as much code probably to use a parser like Bison or other such parser generators. But you could certainly do it, and it would be logically fairly similar structure. And that's where we're going to leave it for today. I think it's super cool. I hope you check it out. I would love to hear about your ventures into CaffeineEight. If you like CaffeineScript, if you want to ask me about writing the JavaScript version, so we could use CaffeineEight but purely in JavaScript. I haven't done that exercise, but all I need is a little bit of interest to push me to do it, and I won't do another video probably, but I'll write it up and I will add it. And cheers. All right, I'll talk to you later. Once again, Shane Brinkman-Davis, in association with GenUI.co, fantastic consulting company I work with, and also my company, imikimi.com. And yeah, adios.